It's not soluble as far as I know, at least not with certainty. But I think I'm going to call it. So, hey everybody, this is just not the Pacers stage at all. So I wanted to talk today about some of the implications of changing SQL, the language, changing the data model underneath SQL, so that it becomes a loosely typed language or a late binding language, depending on how you want to say it. This is a radical change to SQL. It doesn't look like it because you can do some of the same queries as before, but it makes a radical difference to the scope of problems that you can handle and how the actual execution has to work. What I'm going to show today is including a 40x decrease in complexity of a practical database. So my name is Ted Dunning. I'm Chief Applications Architect for MapR Technologies. I'm also committer and PMC member of a bunch of Apache projects. Here's a few. And currently, temporarily, the VP of Incubator at Apache Foundation. All titles like that are temporary at Apache because we try to move things around and spread the expertise and the knowledge about how Apache works as widely as possible. You can reach me all kinds of different ways. Twitter, email, however you like. Come catch me afterwards. So I'm going to talk about a little bit of philosophy. What does good actually mean when it comes to databases? I'm going to talk about what do we mean by loose typing, including some examples of what we can do with a loose typing style in a database. I'm going to show a real database where we see a more than 20x reduction in the number of tables with no reduction, in fact, an enhancement in the understandability of it. And then we'll look forward a little bit about what tools facilitate these changes. So let's do this. So historically, what people thought was good for a database is, one, it had to be expressive enough that all of the important programs could be written. Not necessarily written easily, but could be written. There was expressive capacity in the language. And also efficient. That was very, very important 40 years ago, 50 years ago when databases were first being built. But it's still, to some degree, an important thing because as computers have become more and more capable, we've increased the problem size. So we still need the efficiency similarly as we did in 1972. I'm going to add to this an additional constraint. I think that databases should be introspectable. I think that databases should be understandable on the face of them. You should be able to look at what's in a database and relatively well understand what's going on there. This is becoming much, much more important because much, much more of the data in the internet is coming from somewhere else. I was talking to a retailer a while back. They have 120 subs. They have something like 50 or 100 million stock units. And their subs change the schema of the data that they're sending them on average once or twice a year. That's not an unreasonable rate. But that means they have a schema change every day in the central ID department. And they just have to live with it. That means that they absolutely really need data that they can look at and understand because they aren't even notified when the schemas change, much less given documentation. So introspection is one of the key capabilities that up to now has not been something that we've cared about for big databases. Now, introspection is facilitated when we have fewer entities to discuss. If we decrease the number of tables massively, decrease the number of relationships that are possible, just like in programming languages, information hiding, putting a boundary on the size of a structure made a big difference to how complex programs work. Just like getting rid of the goto and saying flow of control could only transfer a few different ways, that you can't just go to any line in the program, that made programming far simpler and facilitated us writing programs that were massively larger. So those similar efficiencies and advantages apply if we have good introspection, and that's implied by if we can hide things if we don't have to name 20,000 entities, if we only have to come up with a few names, if we can limit the scope of references so that references could only be within a certain circumscribed area, much smaller than a table, and if we can inline relationships where it makes sense, where we have a many or a one-to-many relationship and the many cannot be directly referenced, then why not inline them? There's no reason not to. Now, introspection was never a goal in the 70s and late 60s when Ted Codd was writing the Bible and the whole idea of relational databases. It was never a goal. The goal was mathematical completeness, efficiency, and expressiveness. Introspection wasn't on the list, and introspection was never on the list of results because of that. You only get what you ask for. So we're asking for something new. And the reason that it wasn't really there is because this whole idea of relational databases is a very, very old one. It predates functional programming in the modern sense. It predates logic programming. It predates data structures. I think, what was it, 1972, maybe 1968, when the first theoretical structure of data structures in Tony Hoare's work and Donald Knuth, or not Knuth, Wirth's work, Niklaus Wirth, the whole idea of data structures really occurred about the same time that databases occurred. And practical databases predate practical widespread data structures. Lexical scoping, all of these things, even recursion available in mainstream programming languages, is newer than the core theory behind our databases. Now, this is phenomenal that we have something that old that is still that useful. But the fact is, it's still that old. And it deserves a little bit of update because it's a new world and we have some very exciting things. So I'm going to contrast relational with HBase here on this slide, and then I'm going to augment the HBase side of it with an additional structuring layer, and we can talk about the differences that we get there. So in traditional databases, you have rows with fields, and the fields contain primitive elements. The structure of a database is fixed. You define it. You can do alter table, but it's a very expensive operation. In normal operation, the structure is fixed and totally uniform. Columns exist or they don't. They could have a null value, but they always have a value in a table. No table has the idea of, oh, maybe I'll have a column here in this row, maybe I'll have a column there in that row. That's just a foreign concept. That uniformity is the basis of relational calculus. The structure is also predefined ahead of time before you write data into it. Now, that's been relaxed a little bit in some of the Hadoop programs to do schema on read, but we need more flexibility than that. We need schema during the execution. Referential integrity is a key concept in relational databases. So these are the kind of the underpinnings, and that allows us to build the relational calculus, the relational algebra. It lets us write expressions, programs, that deal with sets of rows and tuples, as they're called in the theory side. Now, HBase and MapRDB are two peas in a pod in that they have rows that have fields, but the contents of the fields are just bytes. And the structure is highly flexible. The number of columns is not a priori known. It can be changed at any time. You can define a new column anytime, anywhere. You can put different kinds of data in there. You can do all kinds of flexible things. There's a single key per row. That's considered a virtue and a defect, and data is considered sorted by that key. Now, they have other features like column families, timestamps, inversions, and stuff. Those are important features for many things. I'm going to kind of ignore them for this talk because they're not really important to the points that we're talking about here. Now, if we add a structuring layer to HBase, we get a few different properties. Suppose that instead of bytes, we actually had something like a JSON model, a BSON or protobuf or Avro. All of these would suffice as a mechanism for building that. But we have primitive elements and objects, which are keys and values together, and lists. And we could have lists of primitives, we could have lists of objects, we could have objects with lists inside, but that's the structuring layer. So instead of just bags of bytes, we have structures in there. That's what we're going to do. And then the structure is still very flexible. It's very ragged. We could have different structures for values in different rows. We could have different numbers of fields, columns in every row. It's very, very flexible, not predefined, still a single key. So that takes us from the relational model to something that I would call a turtle model, referencing the classic comment about it's turtles all the way down, a recursive sort of thing. These complex values that we can have in fields give us some very interesting capabilities. We can, of course, still join anytime we see a key reference deep inside a structure. We can still join to other records. That's not hard. But lists of objects and objects containing uniform lists are isomorphic to relational tables. That means that we can not only put complex structures into tables, we can put entire little tables inside tables. This lets us recurse, so we can have tables that have rows whose values happen to be tables, and inside those, we could have rows that have tables in them. And that's a very far different sort of thing than the standard flat relational model. It allows us to do very, very different things than are normally done with relational databases. It's not the same as having arrays of primitive things. It's not the same as having predefined semi-structured data that we can do a little bit of relational things with. So let's talk about some idioms that we can use in these things. So a first one is we can represent tables either in a row-wise or column-wise fashion. Now, the database does this already. So HBase, for instance, or MapReDB are essentially column-wise, even though they are referred to as columnar. They do not store the data that way. They think of the data in that way. They don't store it that way. So it's more like the row-wise format on the left. The column-wise format on the right, each column is a separate entity instead of each row. Now, in terms of our data structuring, and if we used JSON notation, even if we're not using JSON structure underneath, we can write these as either a list of objects or an object with lists in it. The first is row-based, the second is columnar-based. And these are the ways that we would structure embedded tables inside another table. So we could say that the value kind of to the right on the third row there is in fact a table. And inside of a row-based table, we have a little micro column-based table. So we can get a lot of the virtues of columnar representation without a lot of the vices of mega transformations and things like that. This can be a first-class value that we can then do queries on. That's a big deal. And one of the consequences of that big deal is 1000x acceleration for some applications. I'll talk about those in a moment. So if embedded tables are first class, then the schema becomes data because the embedded table there has a schema, but because data is flexible, we can't really freeze the schema of that embedded data. So the schema itself must become part of our data rather than part of our metadata. And if the schema of subtables is data-driven, and we ever allow those to be promoted to top level, then that means the top level schema also has to be flexible. This is an inescapable logical conclusion. If we don't allow that, then we have nasty, nasty asymmetries in the language where you can do this, you can do this, you can do exactly the same. No, you can't do it here. In the most common case, the top-level tables, you suddenly can't do what you can do on subtables. And that's a vile and mean thing to do to users where you have inconsistencies in what the table can do. So what we've got here is a chain of logic from the embedding of objects to the embedding of tables as objects to completely flexible schema. It is a logical entailment that if we really want objects to be first class, that means we have to do late schema discovery if we're going to have this. So here's an example. This is a real world example. There are thousands of instances of this being run around the world. This is essentially what OpenTSDB does. It uses column names as data. This is another idiom that's common in NoSQL things. So here's how it would look relationally if we were going to store time series data. We might have the time series ID, we might have the sample time, and then we would have a value. Time, value, time, value. It's a time series. If it were stored in a columnar database, it would be pretty efficient. If it's not, it's pretty inefficient. But it's terribly bad because every insert of a data point means another database operation and creates a new row. Those operations are expensive because they're doing things we don't really need in that case. Here's how it's stored in a lot of time series databases that are based on NoSQL. What happens here is we store an entire time window in a row, and the columns are the offsets within the time window. Now this is wacky because the names of the columns are not defined when you start the program. They become known as you collect data. The efficiency here is that when you do a retrieval, you can retrieve an entire hour of data and you get times and values and you have no overhead in the storage there. It's a very flexible and kind of cool thing, but it is distinctly not relational. And in practice, often what happens is we use these concepts together so that over time, as the windows close, as we get to the end of a time window, we go back and pull an entire row and reinsert it as a small column-encoded table into the database. So that columnar table is a table which represents the time series for that entire time window. And so now our retrieval can be even more efficient. And if we insert the data in this form, we can accelerate the operation of the time series database over the speeds that we can achieve with a relational system by roughly 1,000x, if that's how many samples, if that's the order of samples that we put into a single time window. We've achieved, for instance, roughly 300 million data points per second insertion rate on just 8 nodes. This is fast. This is 30 million points per second per node. This is way faster than is reasonable to start talking about transactions going into a relational database. You can do further things because those little micro tables are column-oriented. You can be optimizing and compressing the time elements. Here, for instance, are some experiments I ran for how much could we compress 64-bit timestamps if the samples are taken roughly every 100 microseconds. And if the time-based jitter is small, say less than 5 microseconds, which is typical for a fast sample like that, we only need 3 or 4 or 5 bits per timestamp, and that means that we're getting a 10x or more compression by storing a micro table in there. Yet we still have the flexibility of a row-oriented database in terms of real-time insertion and no reorganization cost like you might have in a pure columnar arrangement. So here's another example. So those are kind of inspirational examples, not a whole lot of detail there. I might be inspirational about this, or I might not be. I might be convincing, I might not be. But here's a real example, and I consider it important because I got shafted by this a while back. I was trying to come up with a music recommender. There's a public domain music database with 16 million tracks in it, all kinds of great information. At the time I was doing it, there was essentially no documentation on it. The database came in multiple overlays that you had to insert into PostgreSQL. There weren't super clear documentation on how those came in. So I had to dope out what all the different things meant. Now, if you think about popular music, it's artists, albums, tracks, maybe the labels, maybe composers and works, but it's really not very complicated. You just have a few things. So artist albums, tracks, and labels are the key objects. There's some details that we might not think about at first because artists have aliases. The artist formerly known as is one of the most formerly known aliases. But you also have compositions, recordings, releases, release groups, box sets or bunch of CDs. CDs might have multiple discs in them. So you have a little bit of elaboration in the structure there. But when you start counting up the tables, 7 tables for the artist, 12 for place, 7 for label, 17 for release and group, it starts adding up. And then you start doing the crazy things like, I want to have relationships between artists and labels, or labels and groups, or release groups. And so you suddenly get a cross product, because with referential integrity, you have to have one linking table for every permutation of kinds of things you link. So if you have 9 things, and you want to link to the same 9 things, that's 81 tables. So the total there, and there's 50 tables that still haven't been documented. Here's a picture of the schema. Well, I lied. Actually, it's 180 tables that aren't even shown on this diagram. This is to talk about, what, 7 things? 236 tables. This is not even unusual. This is not poorly done, and this isn't even the full story. Can you see? I doubt you can. Some of these are in boldface, some are not. The boldface and the not boldface represent things that are split as according to which things are updated quickly, essentially like column families in HBase. So, lordy, it's no wonder it took me 3 weeks, but it should have taken 5 minutes to look at a database about artists, albums, tracks, and labels, and done a query that had a list of the actual names of the artists. It should not take 3 weeks, even without documentation. The database as it was when I encountered it was not introspectable. I couldn't look at it and just get it. Okay, I'm stupid, but how stupid? I mean, this is amazing. This is really much more complicated than it needs to be. Let's see what we can do. Let's take just the artists. These are the 7 tables. 1, 2, 3, 4, 5, 6. Yeah. 7 tables to do with artists. Primary keys, global IDs, which are external things, names, sort names, all the sort of things you'd expect in a realistic database. Well, look at them. The artist type is a one-to-one relationship. The only reason for that separate table is so that we can control the vocabulary. We can control the vocabulary by other means. The gender is a many-to-one sort of thing. It's not one-to-one. There's many people of each gender. It's a table so we can have an open-ended list of genders, which is correct, the way people decide. That's a self-election sort of thing. Then we have IPIs and ISNIs. These are standard international identifiers for artists. We could have many of those per artist because people can re-register for that. Makes sense. But why not inline those? No IPI can refer to more than one artist. And so why not just have a list of those? Well, with all of these sorts of considerations, we wind up with this form if we have data structures. Notice there's a list of IPIs, a list of aliases. We can add a few more fields so that we can have pointers to the objects we haven't talked about yet, like releases and recordings. So if we see this, then what we have are primitive values, just like before. We have one-to-many inlined relations, and we have the equivalent of indexes there in those last ones. And it's much simpler. 7 tables turn into 1. Now, one of those things, like the list of aliases, those are lists of structures. Internally, those things have structures, name, begin date, end date, that sort of thing. But there's no real complexity there because you can just read it and see it and understand it. Let's take a bigger piece. I'm going to do the kind of left 2/3 of this. This is recordings, releases, release groups, albums, box sets, things like that. So what we get there, by similar logic, are 3 tables. So now, at this point, the score is 27 tables reduced to 4. That was pretty quick. It was really pretty simple. It was quick enough, I did most of this today. It's the sort of thing you can do off the cuff. You can just inspect it and do it. It's not hard. But it gets much faster from here. It gets much, much more compressive from here. The 86 link tables can be each replaced by list-valued attributes on the correlating objects. That means 86 tables just went away. 44 tags, ratings, annotations, and everything else can also become list properties. Those 44 tables just went away. All that we had to do is add an attribute. This is really simple. Cover art tables. Well, you have a release, which is a CD. It's the thing that has cover art. And you have a file name, or maybe a list of file names if you've had variant covers. And those are files. So 5 tables just went away. So 162 tables. We're just over halfway done here. It took an hour. Comes down to 4. This is a 40-to-1 complexity reduction. 2-to-1 makes a difference. 40-to-1 is a massive change. This is the scale that we're talking about. And suddenly, this thing becomes simple and easy. If we go back to look at those tables, we have to define the word release. That's a CD or something like it. We have to define a release group. That's a boxed set. We have to define a recording. That's the thing that becomes a track. We have to define an artist. But we're done. All of the things I wanted to do originally are there and more. So this is a big deal. So let's do a little scorecard. Is this good according to the criterion we had before? Is it expressive? Absolutely. It's more expressive than what we had. More expressive in the sense that I can tell you something by writing code. That's expression from me to you. I can express to you the structure. Hal Abelson, famous computer science, said, no, I'm sorry, it was Perlman, but he said that computer programs are primarily intended to convey from one human to another human the content of an algorithm. The fact that they can be executed is a nice side effect, but expressivity here, if you can understand what I've done, is much more important than the other. Now, efficiency-wise, this can be much, much better. It might be a little bit worse because inlining might make things a little bit bigger. But in fact, the common representations for inlining will recapture most of that size. So if we have gender, it looks like strings that are 6 letters long, 4 letters long, that sort of thing. But those will be replaced by dictionary encoding, typically. And so they go back down to 2 bits. So the size doesn't really increase much. And the locality improves substantially. So locality of memory reference, locality of disk reference. Sessionizing, that means, for instance, I capture your metadata, your name, your address, and so on, and then a list of transactions. That means I don't repeat your ID. I just have the transactions. That means I can eliminate repeated data. That can decrease data size as opposed to inlining, slightly increasing it sometimes. We can also inline back references, which makes it more efficient than a normal index and much simpler to understand as well. It becomes like a navigational database instead of a fully relational one. And inline columnar data can save us 1,000x on time and, as we saw, 10x on size. Introspection? I'll let you decide. Are those 4 tables simpler than the 162 tables? Could you even read the text on the 162 tables? Whereas you could read the text on the 4 tables. So just based on the legibility constraint, I'd say this is more introspectable, but frankly, you're the judge here. So what's bad about this? We can't use SQL. SQL is strongly typed. SQL is heavily tied into the original relational model. We can't use SQL as it stands. SQL generating tools require a relational model in order to work. On the other hand, we must use SQL. We can't do without it, and we can't do with it. There's a solution. Apache Drill is a recently generally available project. It just hit the 1.0 version. It's fast. It's not always faster than everything else. It's generally at least even, sometimes a bit slower, sometimes a lot faster. It is SQL compliant in that every SQL expression will mean the same thing in Drill, ultimately. But Drill does this without necessarily having metadata information when you type the query or when the query is parsed. Strictly speaking, you need query typing in order to interpret a SQL query correctly. And Drill still needs this information, but Drill defers the use of that information well into the execution phase. So during the initial parse, it doesn't have all the type information it needs. So it parses that into a thing called the drill logical form, which preserves the ambiguity. Then that is optimized into the drill physical form plan, which still preserves the ambiguity. That's divided up into parallel chunks, these are called fragments, which preserves the ambiguity. So until we're actually processing a batch of records, the final code that actually runs the expressions in the query is not generated until that time. And by that time, the data is in a columnar memory format, and there's a thing called the empirical schema. This is the schema as observed for these records. And now we can generate code. We can generate code that optimizes and vectorizes, uses vector instructions, inlines things, can actually execute multiple statements on multiple records simultaneously within a single thread of control. It's really amazing what you can do if you have the schema information at that point. And in fact, because, for instance, if we have old records where the old column was being used and the new one didn't exist yet, then we later have new records where the old column has been deprecated, is always missing, and the new column is present. In the old stuff, the case statement that we might use to interpret those two alternatives gets optimized away completely because it says, whoa, this new column is always null. I can optimize away the if statement completely. We don't have any conditionals anymore. Boom, that's the data. That turns into a pure reference. That pure reference turns into a no-op. No object creation, nothing. No row assembly, just straight through reference in the compiler. So this is a big advance. This is a big change to SQL, but it doesn't feel like a big change. Where you're doing SQL-y things, it still feels just like SQL. And the trick is you can build views on top of non-relational data that give you nice rectangular arrays of numbers and strings that feel just like relational data, feel so much like it that Tableau or QlikView can't tell the difference. They can hit the views, they get the data that they like, they can slice and dice them, and bam, all the tools work. So this is a big deal. And it comes with nice features. It is parallel, extensible. You get fully parallel execution. You get diagnostics in there. In fact, the diagnostics themselves, each record in the diagnostic log contains the logical plan, which is a JSON object, the physical plan, which is a JSON object. Even though they're very complex graphs, they actually can be stored as data in a row that Drill can then analyze. You get all of the fragments, you get all of the execution histories of all the fragments as little micro tables in there. And so you can use queries to produce results like these pictures. You can analyze the logs of Drill using Drill. It's kind of cool. It's turtles all over again. But you can do more than that because you can join them together so you can do aggregates across classes of queries, all the sorts of things. Now, who here would wait, if you're going to write diagnostics for a program, who here would wait for the DBA team that's in part of your high-speed execution team to change the schema on the logging protocol? The records that Drill drops out for query execution are complex. They would take 50 or 100 tables to describe. And so if we were to store that in a relational form, every time we changed how Drill executes, we would have to wait for some DBA to redefine all the tables, do an alter table on all of history on all people who have tried Drill, and then we'd be able to log it. Who here would wait for the DBA, or who here would switch and just start logging strings? I know what I'd do. I'm not going to wait for the guy. I'm going to start logging strings with a brand new syntax. And we're going to lose all this. We're going to lose the introspection of Drill of itself, the ability to analyze its own performance. In fact, ironically, Impala also drops out JSON doots for performance monitoring, and Impala cannot analyze its own performance logs, but Drill can because they're JSON. So this is a big deal. This is exciting. Here's some examples. So let's find Elvis. Elvis has entered the building. But let's find Elvis, because it's not as simple as it looks, because all of these artists have some arbitrary number of aliases. So we actually have to say, select IDs, artist IDs, and flatten the alias names. So we now get something kind of relational. We can do query-style operations on that. It doesn't actually change the data. It just changes how it thinks about the data. The data is still in columns. The columnar representation has little denotations on it, which indicate this is a list, a repeated value in there. So it's actually still stored columnar. It never even moves the data when we do this flatten. It just changes how it thinks about it. And so then we can do this thing like where the alias is like Elvis Presley. And then we can say, give me all the distinct ID names and alias names from that. Okay, let's do something fancier. Now we want to find the disks where Elvis was credited. So in the bottom part of this query, we find all the Elvises. There might actually be even more than one. And then we join it with all of the credit tags on all of the albums. Credits are also an array of structures, and inside that array of structures is an artist ID, which we can join against the set of artist IDs that we got from people who sound like Elvis. And when we join those, we get album IDs and names of all the albums that Elvis has been on. And I can explain it in 30 seconds, which I couldn't do before, because there were all these tables that were just kind of weird, whereas here, you can look at the table and understand it directly. So what we've got here, the extended relational model allows us to do massive simplifications here. The simplification makes introspection work, and this is good. Drill provides very high performance execution across this very dynamic model in ways that no other SQL engine can do. And you can do it today. You can participate, you can join the Drill community. Anybody who uses it is part of the community and is contributing, especially if they say what's good or bad on the mailing list. So we also provide, I've got the hat on still, so I get to say map our things, provide free online training. We're giving away some free books. I don't know which ones we have available because we ran out yesterday because everybody came and took 2 days worth of supplies when we signed them yesterday. But you can come get some of these. Some of the fun ones, the time series database talks about some of the stuff we said today. The machine learning one for anomaly detection is fun because it has heartbeats in it. You gotta like a book with heartbeats. And the other one has an elephant on the cover. How bad could that be? Thank you. Are there any questions? And we only have, I think, a few moments for questions. And I apologize for running longer than I usually do because the questions are the best part of any talk. Are there any questions about how you can do this or what you'd like to do or anything? Anybody's running out the door to get, yeah. It'll work in just a moment as soon as they catch on that you're talking.
Yeah. I was just, okay, there we go. You had mentioned HBase and then Drill. So I was wondering, how do the two work together? Because Drill could just work with just HDFS, right? Or do we always have to have HBase?
For HBase files, all of those are predefined and can be used, but you can define your own. So one of our SEs took a few days and defined a data source which is a JDBC connection to another database. It took him almost a week to do, but he was actually working during that time. It was evening time. So there's lots of predefined data sources, and you can make more.
And the other kind of attractive feature about Drill, based on my reading, is the idea of storing JSON data and being able to do nested JSON queries. Could you elaborate on that a little bit, please?
I just did. That's what the whole talk is about.
No. I mean, how would you, for example, how would you do time series stuff with JSON, especially?
So with JSON, you would keep a vector of times and a vector of values. And what you would do is you would zip them and then flatten it. Zip like the Python operation or the Scala operation, and then flatten like the Drill operation. That would give me the effect of original relational things with metric ID, time, and value in an apparent table that then I can use in any style I want. Windowing functions, averages, moving averages, groups, any sort of things I like to do, I can then do on that data.
So
Oh,
on
and
that,
by the way, on MapR demos, there's sample drill functions, and there's a zip function there, so you can check it out and try it.
so was that what you were referring to when you were talking about this time series compression at the very end? You would take all the data and basically compress it in that format that you just mentioned.
Yeah, I would use a binary version of JSON that would compress integer arrays effectively.
Okay, thank you.
Sure. Yeah, one more, but this will have to be the last.
How are you building the arrays? So if I had a file, I guess the time series file and then the timestamps were all in a file, how do I get them to, what do you use to build that JSON?
Whatever is collecting your data needs to do that.
Okay.
And the most efficient way to do that is do it at the source as much as possible. But you need to emit those pretty often. And so you may need to migrate that. You may have an in-memory collector that is going against a replayable log so that you can restart the collector. And then you would query the collector, it would give you what's in memory, and then it would also delegate to the database to give you additional data.
So,
One of the books that we talk about talks about how to do exactly that.
Okay,
That's
so-
the one with the guys on it.
okay. So if you were doing it with the record labels that you were doing, would
Yeah.
it be part of the ETL that you do?
ETL, this is a static database, so ETL is kind of a moot point on it. But yeah, ETL might be considered to be batching those things together.
Okay.
Usually you need far, far less ETL with these structures than others. So,
Thank you.
no. I further employed them. I let them rise to their true potential. I didn't unemploy them. But certainly Drill wants to let you play with data as it lies. I call it big data golf. You play the ball the way it lies. Yeah, it doesn't solve everything. Goodness sakes, no.